In this work, we tackle the challenge of making everyday video editing easy and consistent within less than 15 minutes of training. For example, imagine easily applying textures to moving objects, or changing their color across an entire video. We built an idea introducing layered neural atlases, where videos are broken down first into layers, and then each layer is represented using a 2D texture. This technique is known as neural video decomposition. In this setup, every point in the video is linked to a location on these textures. The key insight is that this creates a single unified representation of the video. With just the textures and the layer mappings, we can reconstruct the original video. This makes editing very efficient by modifying a texture and applying the same mappings to changes propagated through the video. In effect, video editing becomes as simple as editing a single 2D image, something you can do in minutes. But there's a problem. Each time you want to edit a new video, you need to retrain the decomposition model from scratch, which usually takes about an hour. To solve this, we introduce HyperNVD, a method that cuts down training time by providing a strong starting point using a hypernetwork. We start from the baseline model HyperNVD, which includes two modules, one for the foreground and one for the background, plus a separate alpha network. The system takes spatiotemporal coordinates x, y, and t as the input. The alpha network decides whether each pixel belongs to the foreground or background, and each module assigns color to the pixel using the corresponding texture. This setup already enables consistent video edits, but training time is still a limitation. That's where hypernetworks come in. A hypernetwork is a network that predicts the weights of another network based on some input. In our case, it predicts the weights of an NVD module using an embedding that summarizes a new video. We use VideoMAE to get video-level embeddings. However, these embeddings are too large to be used directly, so we train an extra MLP encoder that compresses them into a smaller size. This encoder is trained as an autoencoder on the full Davis dataset, making sure the compressed embedding still holds enough information about the video. At inference time, we only use VideoMAE and our encoder to get the final video embedding. This embedding is passed to a hypernetwork, which has 3 groups of MLPs to generate the initial weights. The full pipeline for editing a new video works like this. First, we extract the video embedding. Then, the hypernetwork uses it to predict the initial weights of the NVD module. These weights are then fine-tuned during training, but thanks to the good initialization, convergence is much faster. In our experiments, we showed that this reduces training time from about an hour to just 10 minutes without losing the composition quality. Our results show that the hypernetwork generalizes well across videos, providing strong initial weights that speed up training significantly.